An inductor is a component that stores energy in the form of a magnetic field and as such opposes any change in circuit current. An inductor or inductors are used in many electronic and radio circuits and electrical circuits. For example, radios, filters, audio filters, motor control circuits, etc. In the simplest form, an inductor is simply a coil of wire, and when we start to pass current through a coil of wire, a magnetic field is set up around that coil, and as the magnetic field spreads out, it cuts through different parts of the same coil, producing a restraining force, if you like. It's called a back EMF, which slows the change in current down. And so when we turn an inductor on, the current doesn't instantly go to maximum. It takes some time to reach its maximum value. And a similar thing happens when we turn an inductor off. The magnetic field collapses, and all of that energy that was stored in it now gets returned to the coil, cutting through the conductors, reintroducing an EMF in the opposite direction, slowing down the change in current. So once again, when the current is turned off, it doesn't instantly fall to zero, it slows down over a period of time. An inductor can be as simple as 1 or 2 turns of copper wire, or many turns, normally with some form of core, either a soft iron or, in this particular case like these ones are, it's called ferrite. The unit of inductance is the Henry, used a capital H after Mr. Henry, and a coil is said to have an inductance of 1 Henry if the current through it changing by 1 amp per second produces an EMF of 1 volt. The symbol for an inductor is a series of small hoops like that look a little bit like a coil of wire. The symbol is L, or the letter designation for inductance is L, even though it's measured in henries. And the value in henries of an inductor is determined by the number of turns in the coil and the type of material that's in the coil. If we put an inductor into a circuit and turn the power on, initially no current will flow, therefore the maximum voltage is across the inductor, or the supply voltages, and because no current flowing, there's no voltage across the resistor. Current starts to slowly increase, therefore the voltage across the resistor starts to increase, and the voltage across the inductor starts to decrease. And you can see it follows a similar shape to the capacitors curves, except this time it's the current that increases, not the voltage, as in the case of a capacitor. And when we turn the circuit to the discharge side, current once again has been flowing at a maximum. It will slowly decrease, and the voltage across the inductor actually reverses as the current is flowing the opposite way, and it will then allow the voltage will slowly decrease by this curve as well. Where in the case of an inductor, the time constant, which is the time, if we go back to the previous one, the time taken to reach 1/5 of the time it takes to get to full steady state. So if we take the one time constant, the time to reach one time constant is found by the formula time constant is equal to L over R, where L is in henries and R is in ohms, and it's measured in seconds. And by the same token as with capacitors, that time and one time constant, the value has changed by 63.2% of the maximum. And that's inductors in a nutshell.